we are going to be looking at what we call ionic bonding, an introduction to this very important part of basic chemistry. So in order to get into this, we'll remind ourselves that everything is sort of based on the Weatherford model of the atom, right? This whole concept. So if I just draw an example of an atom, let's take an atom here. Well, let's say that this atom is lithium. Lithium, we know, is number, I have a periodic table here ready to go. So you can see that lithium is over on the far left there, number 3. So it has 3 protons, right? It has 3 electrons. And if you round off its mass to 7 and subtract, it has 4 neutrons. So we can very quickly get the information about how this atom is assembled. And we can put 3 protons here in the middle. We can put 4 neutrons here in the middle. And then we can put the electrons up above in their sort of energy levels, right? So in the first energy level, we would put 2 electrons. And then there's still one more, so we would put it out here in the second energy level. Now, what you have to remember about these energy levels is that the distance away from the nucleus obviously changes. So if you're in the second energy level, then at least on an average, you are further away from the nucleus than you are in the first level. So what that means is that the force that's sort of holding you to the nucleus, the attraction between the negative electron and the positive protons, is a little bit less. So that means that this one electron out here on the outermost edge, is quite far away. And so it's much more easily picked off by something that might have a stronger attraction to it. And that's kind of what happens with atoms, is it's all a matter of, when they meet, who has stronger attractions for electrons, and can electrons be pulled off of one and sort of given to the other, okay? And that's how we look at it. So when we're talking about bonding, we're always looking at the electrons in the outermost shell. We call those the valence electrons. That's the word we use, valence electrons. So you'll want to write that down and put the electrons in the outer shell or orbital. The word shell, orbital are all used interchangeably, or energy level, the outer shell, energy level, or outer orbital, however you want to think of it. You know what we mean by the picture. So those electrons. So lithium here has 1 valence electron. Whoops, let me spell lithium correctly. Lithium has 1 valence electron. And of course, the idea is that an atom is most stable when the electron orbitals are full. So we should write that. We should write that down here. Atoms are the most stable. Now, what that means, we use that word a lot, most stable. And it's a little bit deceiving. I'll put it in quotation marks. Because what does stable mean? Well, essentially what it means is it's the lowest possible energy state that the electrons and the atoms themselves can have. Everything wants to sort of settle down to the least energy. That's kind of the way the universe works. And so what we're talking about when we say most stable is we say a situation or a condition where everything is kind of, less hyper, less energetic, okay? So atoms are most stable when the outer shell is full. Now, what do we mean by full? Well, you'll remember that shell number 1 can hold 2 electrons, right, from our other lecture. You'll remember that shell number 2 can hold up to 8 because it's actually made of 4 little sublevels, right? There's the S and the 3Ps in the new model, in the quantum mechanical model. And so we shortcut that by just saying that it can hold up to 8. So if we're looking at lithium, there's really only two options that it has. In order to get full, it would have to go and find 7 more electrons to put in that orbit. Or it could hand off that 1 electron, which would mean that orbit disappears for lithium, and he's left with the underneath orbit, which is full. The 2 electrons in the first energy level, right? Right here, that would be a full orbit. So getting rid of electrons is one way to do it, or getting more electrons is another way to do it. And so essentially, one of the things that atoms can do to become more stable and form a bond is to find another atom and either give or take electrons from each other. And so that's really the whole point of ionic bonding. Ionic bonding is all about the giving and taking. The giving and taking of electrons. And that's important because later we're going to learn another way that atoms can sort of deal with these issues of having orbits that aren't full. And it involves more of a sharing of electrons. We'll get to that later. But for now, it's the giving and taking that is sort of the trademark of ionic bonding. Okay. So what we should also do is we should look at then each of the atoms that we're going to deal with, and how do we determine very quickly how many electrons they have and how many they want to get rid of or how many they want to take. That's kind of important to know then, isn't it? So then we can look at the Bohr-Rutherford models of each. You'll notice lithium had 1 electron, 1 valence electron, right? And we talked about this before. If you draw the pictures of a few others that are in the same column, right? If I have lithium here, well, sodium is right underneath it. See, it's in the same column, the up and down column. So if I look at that column number 1 and I draw a picture of sodium, we would see that there's a similarity here. Let's take a picture of sodium. So if we draw sodium like this, and of course we would have to look at the table, and we can see that sodium has his atomic number right there, 11. So that means it has 11 protons and 11 electrons, right? And then this number is the mass. It rounds off to 23. And if we subtract 11 from 23, we're left with 12. So there are 12 neutrons, right? 11 protons, 11 electrons, and 12 neutrons. So we can go back here and we can write in those things, okay? So in here we have 11 electrons and, protons in the nucleus. Ooh, big mistake there. We don't want to make that mistake, do we? 11 protons in the nucleus and 12 neutrons in the nucleus. And now we have to put the 11 electrons in their proper spots. And so we do that by putting 2 in the first orbital, because all it has is the S shape, right? There's no P shapes on this orbital. So there's just room for 2. And that would leave us with 9 more, right? So the next ones would go above, but only 8 can fit here in the 2s and the 2px, 2py, 2pz. That's 2, 4, 6, 8 electrons, right? And we're still left with 1 more, because that's only 10. We need 11. So the next one would have to go in the 3rd energy level or shell. So this is the valence electron up here. This is the valence electron. And you'll notice there's 1 valence electron. It's the valence electron on the outside of the atom. It's the same number as lithium. And that's important. And so if we go back to our periodic table, we see that lithium and sodium, let me just grab the eraser for a second and erase some of that stuff that's in the way there. Lithium and sodium are both in the same column because they both have 1 outer valence electron, even though they have different numbers underneath, right? Going back here, there's 10 electrons underneath here for sodium, and there's only 2 electrons underneath for lithium. But on the outside, they are the same, right? And so that means, that's why they're in the same column on the periodic table. If we were to draw a picture of every atom in the first column, we would find that, go back to my pen, we would find that every single one in this first column would have 1 valence electron. All the ones in the first column. And so we call it the +1 column. Okay, +1. Actually, I'm going to get a thicker line here. I don't like that one. It's a little bit too thin. So the +1 column. Now, remember why we're calling it +1. Okay, why not -1? You'd think, well, if you have an electron in your outer orbit, that's a minus, right? But the whole point was that for these atoms, for lithium and sodium, and everybody else in this column, we decided that rather than try to find 7 more to fill this up, it's a lot easier to just get rid of the 1. So all of these atoms, basically their mission in life is to get rid of 1 electron. That's their goal. Get rid of that valence electron and leave all the nice full shells underneath. And so if you're getting rid of a negative electron, you become more positive. You see, there are, if we count right here, if you get rid of this one, you're left with 10 minuses, but you still have 11 pluses. And when you put that together, the difference is +1. And so we say that if this atom of sodium here was to get rid of 1 electron, it would have a charge of +1. That would be its charge overall. The difference between the protons and the electrons is no longer the same, or 0, right? Now it's +1. And we call it an ion. That's the word for a charged atom, once it's given away its electron. And some of this you will remember from grade 9. You touched on these ideas in grade 9. Okay. And so, if we go back to our periodic table, we see that everybody in column 1, all the way down, and if I, I don't know if I can move my table without, perhaps if I do, nope. Anyway, everybody in this column, all the way down the table, including hydrogen, he's here too because he has 1 electron. And what's weird about hydrogen is he kind of has double options. I'll talk about him in a minute. All of these guys that I just put in blue are all in the +1 column because they all will try to lose that outer electron right there. They all have it, and they will become a +1 ion. Okay? So that's why that column is called +1. Now, hydrogen is kind of interesting. If we just look at the hydrogen atom quickly, whoops. Hydrogen is simply 1 proton and 1 electron, right? 1 E in the first orbit. So to get full, hydrogen could grab another electron and make this top orbit 2. So he could take 1 from somebody else. Or, amazingly, he could just get rid of the one he has and have no electrons at all. Sort of like he runs around naked as a little proton. And hydrogen doesn't seem to mind this. It seems to be a very stable arrangement for hydrogen. And so quite often, hydrogen will give its 1 electron away and form a very stable bond with other things. But hydrogen doesn't often bond ionically very much. A lot of the hydrogen that we're going to see, hydrogen is very unique because it's simplicity, right? It's a very simple atom, and it can do some really cool things because it's small and simple. And when you get on into biology, you're going to see that hydrogen is a very important atom for biological molecules and things. We haven't even talked about molecules yet. Okay, the things we're building here are not going to be molecules because molecules are not ionic bonding. And so we're just talking about ionic bonding, so we'll leave hydrogen out for now. So you can kind of ignore them for now. We're going to deal with lithium, sodium, potassium, and of course we could also do rubidium and cesium and francium if we wanted to. They just are so big, they're a pain to draw because they have lots of electrons underneath. It's just easier to do the simpler ones when we're drawing pictures. So they all follow that rule. Okay, now, I'm not going to draw every single picture, but I will draw one more. I'll draw a picture of, let's go over back here. Let's go to this guy. Whoops, I still have my eraser on. Let's go to this guy right here, beryllium. Right? We're going to draw him. He has 4 is his atomic number, so he has 4 electrons and 4 protons. This number rounds off to 9, and so 9 take away 4 means 5 neutrons, right? Everybody's got that down pat from grade 9. So we'll draw his picture, okay? Let's go over here. So 4 protons, let's put those in the middle. 5 neutrons. Now, the electrons, well, there's going to be, let's change our color here. There's going to be 4 of them, so 2 go here. The other 2 must therefore go up into the next level. And you'll notice that he has 2 valence electrons on the outside. And so for him to get full, he either has to find 6 more, which is harder, or just get rid of those 2. So most of the time, he will simply get rid of those 2 electrons right there. And when he does that, he will become charged. If you count the pluses and minuses, you'll notice that the 4 pluses here and the 2 electrons left over means he'll have a 2 plus charge. A 2 plus charge because he's giving away 2 negative electrons in order to get full. 2 plus charge. Okay, and that means he becomes an ion with a charge of 2 plus, positive 2. In chemistry, we tend to write the plus sign after the number. In math, you would write, positive 2, negative 2. But in chemistry, we've adopted this formation or this convention of writing the plus after. It's not really super wrong if you do it the other way. It's just sort of a little bit of bad form, and some teachers might get upset. So try to practice writing your charge sign after instead of before the number. And the other thing we do as a shortcut is when the number is 1, we often just write the little plus or minus sign. We don't actually show the 1, just to make things faster, I guess. But the key thing here to remember is that this little beryllium has 2 valence electrons right there. And if he gives them away, he will become a 2 plus ion. And that means if we go back to our table, we could call this the plus 2 or the 2 plus. See, I put plus 1 over there. I should have put the plus on this side to be a good chemist, right? That's what happens when you have a physics teacher who's teaching chemistry. We do things backwards. 2 plus, though, is the number here, or the ion that all the people in the second column will form. If I draw a picture of magnesium, he will have more electrons, but there will still end up with 2 on the outside. And the same with calcium, if we drew all the pictures. So that's what the 2 plus means. It means that all these atoms have 2 electrons in their outer orbit, or you could say they have 2 valence electrons, which they want to give up, which when they do, would make them charged in a 2 plus way, positive 2. And then we can carry on with this pattern. Without drawing all the pictures, you can kind of just trust me. We're going to bypass all of the transition metals here. We're going to skip all of this, and we're going to jump across to the next column. Okay? You'll notice on the table that they have little titles here. They have 1 and a 2. See the 1 right here and the 2. They also have a 1A and a 2A. And you'll notice that 3A is over here. And down here, they start calling them 3B, 4B, 5B. That's because it's a different section of the table. And these atoms down here, in order to draw their pictures properly using the new quantum mechanical model, you have to study all the rules of how the electrons fit into those orbitals. And it gets a little scary. So for today, and for now, for ionic bonding, we're just going to look at sort of the ones that are that are easier to understand. So we're just going to skip over those. And the reason that this 3A is over here is because this pattern that I'm talking about of +1, +2, it carries along the A part of the periodic table. So over here, if you drew a picture of boron, you would find that it has 3 valence electrons. It wants to get rid of those 3 electrons, and so therefore this would be the 3+ column over here on this side. And everybody in this column would form a 3+ ion if they were giving away their valence electrons. Okay, now we get to carbon. And now remember, the reason they're giving away 3 is because giving away 3 is simpler than trying to find 5 more, because you have to fill up to 8, right? But what happens with the next column is carbon. You'll see that it has 4, right? In fact, let's draw a little picture of carbon just for fun. It has 4 electrons in its outer orbit. So here's carbon. Carbon is number 6. So it has 6 protons. It has 6 neutrons, and I'll just keep the same color for now. It has 2 electrons and then 4 electrons. Well, if you look at the valence electrons right here, to get full, you could either add 4 or take away the 4 that are there, and it doesn't seem to be any preference, right? What's harder? Add 4, get rid of 4. So carbon tends to be able to do both, give away or take, right? And it depends who he's with. It depends which other atom he's with. If carbon is hanging out with an atom like lithium who is +1 and wants to give away, then he'll take. But if he's hanging out with another atom like something that's a little that wants to take electrons, he might give them. Okay? So what we say for carbon is he's plus or minus 4. He could take away these 4 and become +4. Right? Take those away. Now he's +4, like that. Or he could keep those 4. He could keep those 4. Let me just see if I can erase. No, I guess not. Let's go this way. He could keep the 4 that he had and try to find 4 more and turn into 8. Well, if you add 8 electrons extra, then you're going to have, look at the numbers here, 8 and 2 is 10, and only 6 pluses, that would be the -4. So by giving away electrons, you become positive, but by taking electrons, you become negative. And carbon can do both. So it all depends on who carbon is with. Now carbon, because it can do both, is also very weird, and it does some pretty amazing things. Carbon is one of the most important atoms in the building of biological things. People like you, and dogs and cats, and oak trees, and little squirmy worms, and all the things that live depend heavily on carbon. You'll find carbon everywhere inside living things. And that's because living things can become so complicated and do so many cool things because carbon can do so many cool things. And when you study that in grade 11 biology, in grade 12 biology, you'll see the amazing things that carbon can do. Okay, so that means that over here, where carbon is, it's the 4 plus or minus column. It's kind of got dual duty. It can give away 4 or take 4 electrons. All right. So now, I wonder if I can move this over on my computer. Oh no, whoops. There, that seemed to have worked. Now we can see the other side. Okay, what happens though is all my numbers are gone or mixed up. So what I'll do is I'll go back to my eraser for a second and I'll just erase everything and I'll put it back on here where it belongs, because when I move the sheet, it moves over. So here's what we've got so far. Let's go back to my red and there. Da-da-da. Okay, so this was the +3 column. Now I should put 3 plus, right? Chemists. And the 4 plus or minus column. And now, of course, the next column is nitrogen. So what number would it be? Well, this is where everything sort of reverses. Because if we draw a picture of nitrogen, let's draw that picture really quickly. Nitrogen, right? Well, let's go back. Nitrogen is number 7, so it has 7 protons. And then it's 14 here, so you subtract that and get 7. So it has 7 neutrons. So it has 7 of everything. It's one of those ones where everything matches, which is handy. So it has 7 protons, 7 neutrons, and 7 electrons, 2 in the first, the rest go up above. So now it has 5 in the outer orbit. These are the valence electrons of nitrogen, right? Valence is an old word that means sort of to hold hands or to grab. That's why it's called that. And that's because these atoms are giving these electrons away as they form their bonds, right? So what's easier, to fill up by finding 3 or trying to give away all 5? It now becomes easier to take electrons rather than give them away. So nitrogen is not going to lose 5 electrons and turn into a plus ion. What nitrogen's going to do is try to add 3 more so that it gets to 8 in that top outer shell. And if you add 3 more electrons and then you count them all up, you'll see that this adds up to 11 minuses. But down below, there are only 7 minuses, or sorry, 7 pluses. And when you subtract, oh, I'm sorry, I did that wrong. That's 10, isn't it? On the top, right here, 8 and 2. Is 10. And then 7 down below, when you do the difference, the overall effect is 3 minus, not 3 plus, but 3 minus. You can think of it this way. We added 3 negative electrons to fill it, so that's 3 minuses added, so obviously it would be 3 minus. So that means now we're talking about minus ions, who are the opposite charge. That's what happens when you get past carbon. So nitrogen is the -3 column, or 3 minus, and everybody is 3 minus in that column. And then if we carry this pattern forward to oxygen, we'll find out that oxygen, who has 6 electrons in his outer orbit, needs to find 2 more. It's not going to give away all 6. So we're going to add 2 electrons, which makes it adding 2 minuses, right? You're adding 2 negative electrons, and oxygen will be the 2 minus column. And then if we draw the picture of fluorine, fluorine has 7 electrons in its outer orbit, which means it only needs to steal 1. So you're going to add 1 negative electron to make it 8, and that means this is the 1 minus column. And so these little numbers now that we've drawn are used to be a shortcut for how to figure out the kind of ions they will form and how they will lose or give electrons, right? Fluorine will form a -1 ion. Carbon will form a 4 plus or 4 minus, depending on who it's with, because of this number. Aluminum will form a 3 plus ion, and so on. So now we have a pattern and a shortcut to help us out without having to draw the pictures every single time. But it's critically important you remember what these numbers mean. When we have a shortcut, we sometimes forget the long way. And that's not good, because the shortcut is just meant to help you go faster. You still need to understand what's going on, okay? All right, so now we can talk about the formation of ions, which is when the 2 atoms get together. So let's go back to our little picture here, and let's go down a little bit. Let's make a little subtitle, and we'll call it the formation of ions. Okay? And I'll draw one with the pictures just to show you. We'll do lithium because he's the easiest one to draw. There he is. 3 protons, 4 neutrons, 2 electrons, 1 electron. That was the picture of lithium. Okay, and I'll even write his name down here just so we remember who we're talking about, lithium. So what happens is, if you look at the valence electrons, to get full, lithium wants to lose 1 valence electron. And that will make him full. That will make the, well, I say full, It sounds like if you lose something, you should get empty. But what it means is underneath, down here, he's got the full 2 electrons. See? If he loses the outer one. So he wants to lose 1 valence electron. That means he will form a +1 or 1+ ion. If he does that, he will become charged and he will be called an ion, a 1+ ion. Okay? If we do another example, let's say we do oxygen. Here's oxygen. Well, remember, oxygen has already 6 electrons if you draw his picture. So we'll quickly draw his picture just to show what we mean, right? So here's a picture of oxygen. Oxygen has a nucleus, and he has 8 protons, 8 neutrons, 2 electrons here, and then he has 6 electrons up here in the second orbit. So what he's going to do is not lose all 6. It's easier for him to gain or to take 2 electrons, 2 valence electrons, I'll write that one, 2 more valence electrons, because that will make him fill up to 8 right here. If we add 2 more in, see, he's full. That means he will form a -2 or a 2- ion. And of course, that's why on his column, it's -2. Okay. So far, so good. So now all we have to do is put together what happens when an ion that's plus comes near to, or an atom that forms a plus ion wants to sort of get close to an atom that forms a minus. You can already guess that in order to form some kind of bond, you have to have a plus and a minus, because you know that pluses and minuses attract, right? That's one of the main rules of the universe, is that positive charge is attracted to negative charge. Why that actually happens is quite complex, and you'll learn more about that in grade 12 and if you pursue physics in university. But for today, we'll just use that simple rule. 2 minuses would not get together, would they? 2 pluses would not get together. They would repel each other. So we never see sodium trying to hang out with potassium, because both sodium and potassium are way over on the other side, right? I wonder if I guess it doesn't matter what I do to this. It's still going to be, yeah, I'm going to have my, got to erase all my drawings here for a second. We'll use the whole table in this form for now, just so you can see what I mean. Sodium and potassium would never get together because they're both over here. They're both forming a 1+ ion. So 2 pluses could not get together. So you always need to have one of the plus ions, which happen to be over on this sort of left-hand side of the table, going together with the minus ions, which are over here. It's the only way you can form a bond. And now all we have to do is figure out how the numbers will work. Okay, so our next, we're going to stop this video because we've gone on quite a bit already. We now know how they form ions. We'll stop this video and we'll do a second video after we take a short break on how they actually get together. Okay.